Hey there, this is Chipmunk Math. I'm Vince, and in this video we're going to get an advanced understanding of the Pythagorean Theorem. In the video lesson, we saw the Pythagorean Theorem, but we didn't see why we should believe it's true. So in math, if we want to show that something always has to be the case, we have to give a proof. We have to give something that shows logically that it always has to be the case. So let's prove it. Let's see a proof for the Pythagorean Theorem, why we can trust this thing. Now, what we're going to see here is just one of many different possible proofs. There's a huge number of different proofs for the Pythagorean Theorem, so we're just going to see my personal favorite way to prove the Pythagorean Theorem, and I hope you like it. All right, so let's start off with just any old right triangle. Say we've got just some right triangle, and we'll call the sides A and B for the legs and the hypotenuse C, just like we're used to, and we've got a right angle, because it's a right triangle. So if we've got this set up, what could we do with this? Well, instead of just having one of the triangle there, we could make more of them. So we have 4 of these right triangles, right? So we've got 4 identical copies of this right triangle that we started off with, but we're not just going to leave them out anywhere. We're going to make a special shape with them. We're going to move them into this square shape. Now, it certainly looks like a square, but how can we be certain that it's a square? Right? Well, first, we see that it has right angles in all of its 4 corners because of those right triangles we made that shape with. But even if it has those right angles, we can't be certain it's not a rectangle, right? How do we know for sure it's a square? So to be sure of that, let's bring in all of those side lengths again. We see those side lengths here, and now if we look at that outer shape of the square, we notice that all of the outer sides of that square are A and B, right? It's both of the side legs from that triangle we started with put together. So all of our outer shape square all have side lengths of A plus B. So we've got right angles and we've got matching side lengths all around that outer shape. So we do definitely have an outer square. Now, on the inside, it certainly looks like we have a square as well, right? We've got C, 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 C. We've got those 4 sides. They're all the same. But once again, we've got the same kind of problem. We can't be certain that we have right angles in there. So how can we be sure that we're looking at a square and not, a squished rhombus shape where it's got all the same side length, but it isn't actually a square because it lacks right angles? So to figure that out, let's go back to that triangle that we started with, right? If we consider that triangle, remember how many angles are inside of a triangle? And sorry, by angles, I don't mean the 3 angles. I mean, what's the sum of the 3 angles inside of a triangle? It always sums up to 180 degrees. So if we know that it adds up to 180 degrees and we've got that right angle that's already 90 degrees, if we subtract that from the 180, what remains is 90 degrees. It's got to be the case that the other 2 angles inside of the right triangle add up to 90 degrees. Now, if we look at where those other angles show up in that big square shape we made, we see that they wind up matching nicely around the corners of that inner square shape, right? They all show up because of the way we placed those triangles in the first place. And so notice, because that outer square has straight lines making it up, we've got both of those angles on a 180 degree line, right? A line makes an angle of 180 degrees, so that inner square shape for all of its corners has to be the remaining 90 degrees to make that 180 degree line, right? We know those 2 angles from the triangle add up to 90 degrees, so what's got to be inside is another 90 degree so that we can add up and make a straight line of 180 degrees like we set it up. So at this point, we have our right angles on the inside, so we do have a square shape on the inside, we have a square shape on the outside. This is a pretty great thing. So what can we do with this? Well, notice there's 2 different ways of looking at this thing. We've either got a big square, or we've got a smaller inner square that's surrounded by triangles. So because we have these 2 different ways of looking at it that still are the same thing, we can consider the area of these 2 different situations, right? We consider what's the area of that big square, and we know that the area of that big square has to match the area of all 4 triangles combined with the area of that inner small square. So another great thing about this is because all 4 triangles are identical, instead of saying the area of all the triangles, we can just say 4 times the area of one triangle because it's just 4 copies of the same triangle showing up. So what is those values going to be precisely? Well, the area of the big square, remember its side length was A plus B because it had both of the legs from the right triangle making up its sides. So we've got A plus B squared for the area of the big square. And then the area of the triangle, well, area of a triangle is 1/2 base times height. So we've got 1/2 A times B. There are 4 copies of it, 4 times 1/2 AB. And then finally, what's the area of the small square? Well, it's got C for all of its side lengths. So we've got C squared there. So at this point, the great thing about this is we've got this nice equation that we can really get into working on, right? We can do some algebra with this equation. Maybe we can get something to come out of it. Some nice expression will come out of it. And so we start working with this. We've got A plus B squared equals 4 times 1/2 times A times B plus C squared. So a plus b squared, well, we can just write that as a plus b times a plus b. We simplify on the right side, 4 times a half ab. Well, 4 times a half, that becomes 2, so we've got 2ab plus c squared. What's a plus b times a plus b, right? We're sort of foiling that out. If you're used to the word foil, we're just expanding those two chunks, those two quantities. A plus b times a plus b, that's a times a squared, a times b, ab, b times a, ba, b times b, b squared. On the right side, we've still got 2ab plus c squared. Hey, on that left side, ab and ba, those are really just the same thing, right? Because we're just changing the order of multiplication, but that doesn't mean anything with these numbers. So a squared plus 2ab, right? We combine those together into 1, plus b squared equals 2ab plus c squared. Hey, would you look at that? We've got 2ab showing up on both sides. So we can use algebra at this point. We can subtract 2ab from both sides, and what remains is a squared plus b squared equals c squared. What do you know? A squared plus b squared equals c squared. It's our old friend, the Pythagorean theorem, right? That's the equation that we were trying to get in the first place. And now the great thing about this is this logic works for any right triangle. When we set this up, we purposely chose a right triangle that wasn't special in any way. We chose a right triangle where we didn't really know anything about it. We just said, yeah, let's call the sides, A and B for the legs, and we'll call the hypotenuse C, and let's just sort of see what we can do with it. So because we didn't have anything special for this right triangle, this logic works for any right triangle. And because it works for any right triangle, it's got to be the case that a squared plus b squared equals c squared for every single right triangle that's out there. And that's it. We've managed to prove the Pythagorean theorem. Pretty neat. Back in that video lesson, we also talked about the idea of the Pythagorean converse. So let's motivate a way to expand on the idea of the Pythagorean converse. So start off by thinking about a right triangle, right? A just good old a squared plus b squared equals c squared right triangle. But what would happen if we wanted to stretch c out a bit longer, but we wanted to keep that base in place, right? We didn't want to move a, we wanted to keep it locked in place, but we wanted to stretch out c. Well, what's going to happen in that case is we're going to lose that right angle and it's going to get bigger than 90 degrees. And also because c's gotten larger, that a squared plus b squared equals c squared, that's no longer true, right? The c grew on us, so now it's a squared plus b squared is less than c squared, right? The c squared is the big part now. What if we went back to how we started, a squared plus b squared equals c squared, but this time instead of having the c get longer, this time we make the c shrink down some. Well, in that case, we lose that right angle, and now it becomes less than 90 degrees. And because c just got smaller, instead of it being a squared plus b squared equals c squared, it's now a squared plus b squared is greater than c squared. So this brings us to the Pythagorean converse with inequalities. Instead of just testing, is it a right triangle or is it not a right triangle, we can now find out what type of triangle it is. So for any triangle that has side lengths of A, B, and C, where C is the longest side, we've got these three possibilities. A squared plus b squared equals c squared means that it's a right triangle, right? This is the one that we're most used to. But beyond that, we also have that if a squared plus b squared is less than c squared, then we're looking at an obtuse triangle, right? If c has gotten to be the big side, then it means that the angle opposite has to grow larger than 90 degrees. And remember, an obtuse triangle is just any triangle where one of the angles is bigger than 90 degrees. And then finally, if a squared plus b squared is greater than c squared, right? The c got the small part, then that means we're looking at something where the 90-degree angle that would normally be there shrank, and now we're looking at an acute triangle. Remember, acute is a triangle where all of the angles are less than 90 degrees. So those are our three situations. So we can look at any triangle now with A, B, and C, where C is the longest side, and we can just figure out which of these three situations we're in, right? A squared plus b squared, is that equal to, smaller than, or greater than c squared? And depending on which of those three situations, we know if we're looking at a right triangle, an obtuse triangle, or an acute triangle. All right, so let's see an example of this, right? Say that we've got a triangle that has 5, 6, and 8 as its three sides. The first thing you need to do is you need to identify which is the longest side. So 8 is the longest side here, so we say c equals 8. The other two sides are going to be our a and our b, so we have a equals 5, b equals 6. At this point, we want to compare the a squared plus b squared against the c squared. So a squared plus b squared, compare against c squared. And I've got those question marks there because I don't want us to think that it is equal or less than or greater than. We just currently don't know. We're trying to figure out what is the situation. So we're just figuring out what's a squared plus b squared, and we're figuring out what's c squared, and then we'll compare the two against each other. So a squared plus b squared, 5 squared plus 6 squared, and then c squared, that's 8 squared. 5 squared is 25, 6 squared is 36, 8 squared is 64. What's 25 plus 36? We get 61. Hey, 61 is less than 64. So what we have here is it's a squared plus b squared is less than c squared. C is the big part, so that means we have something bigger than a 90-degree angle. We've got an obtuse triangle because we've got something bigger than 90 degrees. All right, finally, let's say a proof of the Pythagorean converse. At this point, it seems pretty reasonable, right? If we know that if it's a right triangle, it has a squared plus b squared equals c squared. but we aren't absolutely certain that a squared plus b squared equals c squared implies that it is a right triangle. So in math, we want proof. We really want to be sure of these things. So let's prove it. Let's see the case that the Pythagorean converse is true. So remember, just let's have a quick reminder that what the Pythagorean converse strictly is. It said that if we have a triangle where a squared plus b squared equals c squared, then we know we're looking at a right triangle. All right, so our given here is we've got some triangle with sides of a, b, and c, where c is the largest side, and we know that a squared plus b squared equals c squared. And I want to point out, you don't know what the angles in this triangle are, right? You have no idea what the angles in the triangle are. All you know is that a squared plus b squared equals c squared. It's our job at this point to show that there's some way to figure out that it has to have a right angle in there, that it actually is a right triangle we're looking at. So for this, we're actually going to do this kind of interesting thing. Instead of considering what we've got right in front of us, we're going to build a new thing. So let's construct another triangle. And what we're going to do is we're going to copy pieces from the old triangle. So we're going to copy that length of A, that side A, and we're also going to copy that side B. So now we've just got two different line segments, A line segment and B line segment. Now, what can we do with them? Well, we can really do anything we want with them. So let's put them together at a right angle. So now we've got our two line segments connected together at a right angle. A and B matching the sides from that original triangle. So look at that. Well, if we wanted to, there's nothing stopping us from drawing in a third side and making a triangle. So at this point, let's draw on that side and let's call that side X. So at this point, we've got a right triangle, right? Because we put A and B together at a right angle on purpose in our new construction. So we're looking for sure at a right triangle. Now, because it's a right triangle, we can use the Pythagorean theorem, right? Anytime you've got a right triangle, you can use the Pythagorean theorem. So we use that on our new triangle, and now we have that a squared plus b squared equals x squared for this new triangle. Now notice, a squared plus b squared, we can use substitution, right? From our given, we knew that a squared plus b squared equals c squared. So we can plug that into the a squared plus b squared equals x squared, right? We swap a squared plus b squared for the c squared we know from our given, and now we have c squared equals x squared. And since c squared equals x squared, and we're talking about lengths that have to be positive, it's got to be the case that c equals x. So now we know that the side length of c matches the side length of x. And this is great because since we know that c equals x, we now know that all the sides of our two triangles, our original starting triangle and the newly constructed triangle we just made, all those sides all match up. All three sides are congruent to each other. So by side congruence, right? If you've got two triangles where each of the three sides are congruent to the other three sides in the other triangle, then you know that the two triangles are congruent to each other. And if you've got two triangles that are congruent to each other, you know that all the angles have to be congruent as well. So that right triangle for our new construction, that right angle in that new right triangle, hey, that's got to copy over to the original one. It was already there in the original one as well. We're just finding that out now. So the original triangle had to have a right angle as well. Boom, now we've managed to prove the Pythagorean converse as well. Pretty neat. So at this point, we managed to lock down the Pythagorean theorem and the Pythagorean converse. Really powerful stuff here. Cool. All right, that wraps things up. Thanks for watching, and don't forget to check out the other videos at chipmunkmath.com on this topic. I especially recommend if you were watching the Advanced Understanding, you might like to check out the Pythagorean triples video. It's kind of interesting, and it's also really useful if you're going to be taking any standardized tests, and it's useful on tests in general, but especially if you're taking standardized tests, it can give you a little bit of an edge. All right, see you next time.